Hello again, my name is Marissa Butillo, and here's my presentation on deriving the Michaelis-Menten equation, which is used to quantify the effect that substrate concentration changes have on the overall reaction rate for enzymes. So let's start with our end goal here. All right, for the Michaelis-Menten equation is given as V null, V max times the substrate concentration divided by Km plus the substrate concentration, where V null is the initial reaction rate, V max is the maximum velocity when all enzymes are bonded to substrate. As a side note here, we know that V max, where K2 is the kinetic energy needed to produce product, we'll go a little more into that later, and bracketed E sub T is the total enzyme concentration. Back to this, we know that Km is the Michaelis constant, which is the amount of substrate concentration at which reaction rate is equal to half of V max, and Km can be solved with the following. We're going to start deriving the Michaelis-Menten equation by looking at two simple steps in the overall reaction. One, so in this first step, showing that enzyme and substrate combine to form the Michaelis enzyme substrate complex, ES. And this reaction, even early on, proceeds forward, shown by rate K1, and backwards, shown by rate K to the minus 1. And step 2, the second step here shows the enzyme substrate complex splitting into enzyme and product. And at this stage of the reaction, we're only considering that forward reaction rate, K2, as there's not yet enough product to have a substantial backwards path taken into these enzyme kinetics. So this is also going to be that K2 that will come into play in the Vmax equation. So written together, the reaction will proceed as follows. And if we were looking at a later portion of this reaction, that K2 would have the same forwards and backwards K2, K to the negative 2, but we're not going to consider that for derivation of the Michaelis-Menten equation. So using these two steps, we can write out the steady state approximation as instantaneous rate of change for ES over dt. And this just shows that the creation of the enzyme substrate complex is equal to the sum of reactions decreasing its concentration. Let's go ahead and write that one out. And this is using components from above. So let me just go ahead, I'll break those down a little further, kind of highlight what we're doing here. This comes from that rate K1 and the backwards reaction. And here's taking into account that second step. So now we're going to focus on finding the value of unbound enzyme. So we'll use the equation E sub T here again, E sub T is the total concentration of enzyme. We just have that bracketed E is the concentration of unbound enzyme, and this is going to be what we're looking for. And the ES is the concentration of the enzyme substrate complex. Let's go ahead and rearrange this so that we can solve for what we're looking for. And then substitute that up into that bigger equation, and we're going to replace the E. And our goal is to get the ES, so we're going to go ahead and do some factoring and distribution to try to solve. Sorry. Okay, break that down a bit further. And then we're going to multiply the top and the bottom both by 1 over k. Now using the equation for instantaneous rate of change for products, I'll go ahead and I'll write that one out here. We're going to sub in this new equation we found for ES to get a velocity reaction for when V null equals this. So let's go ahead, I'm going to sub that into there. And we'll get the reaction. Sorry, I realize I'm a little out of screen here. To break this down even further, we have to sub out this K2 and this in the parentheses using some previous equations. Go ahead. Give myself a little more room to work. Okay. So for the bottom part, this one's going to be a simple substitution here. We can go ahead and use that Michaelis constant equation. So we can see easily how that's going to sub right into there. And to sub out this top K2, we're going to need to know that in the Vmax equation, I'll write that out again. That this K2 is also equal to K cat, or actually the turnover number, and that's the number of molecules an enzyme can convert into product per 1 unit of time. So we'll say that K2 is equal to that K cat, and it's also equal to the turnover number. So we're going to go ahead and put that guy up there also. So with these substitutions, that'll yield V null. I'm going to use K cat here. Remember, that's the same as K2. And we also know, again, we'll look at this, Vmax equals K2. So if we're just going to keep that going, and that'll be our last substitution, we can go ahead and get the final Michaelis-Menten equation here. So we are back to the starting point, Michaelis-Menten equation. Sub in that Vmax times substrate concentration. And there we have it, our derived equation. Just gotta make sure we get more room. And the last thing we want to do here is go ahead and check our work, and we can do that with some simple knowledge of Km. So we can say that since the Michaelis constant is equal to the substrate concentration at which the reaction rate is half Vmax, then in that instance, Km is equal to the substrate concentration. So we're going to go ahead and plug that back in. Phenol. That'll be over 2 times the substrate concentration, which would give us Vmax divided by 2, or half Vmax. So this confirms that when Km is equal to the substrate concentration, that the rate is in fact half of Vmax. So that go ahead and confirms what we know there. So what do we know from all this? We know that if Km is low, only a small amount of substrate is needed to reach half of Vmax. So the reaction should approach Vmax rapidly, and the enzyme has a high affinity to bind. Now if Km is high, you need a lot of substrate to reach half Vmax, meaning that the enzyme does not bind as efficiently to the substrate. So half Vmax is only going to be achieved when substrate concentration is very, very high. So thank you for watching my video. Hope you enjoyed. Hope you can read my handwriting. All right, bye.